We now look at a problem that involves the normal approximation of a binomial distribution. In this problem, we have 50 trials, 50 students, and the probability of success, quote unquote, of making a mistake is actually 60%. And the question is finding the probability of between 25 and 33 students inclusive that have errors on their first assignment. And so I'm looking for the probability of getting a count that's between 25 and 33. I will use the normal approximation to estimate this probability, so that converts from a binomial distribution k to a normal random variable x. And x will range between 24.5 and 33.5. I use a binomial distribution. The normal approximation is approximating a binomial distribution. That is the one and only time that in this course we'll be using the 0.5 business. So because I'm approximating a binomial, the rectangle that's on 25, the left endpoint will be 24.5. So if I imagine kind of a quick picture down here, here I have 25 would be, there's a rectangle at 25, a rectangle at 26, and so on, leading to a rectangle at 33. And the probability on the left would be found by adding up the areas of these rectangles. Well, the left edge, I'm counting all of these rectangles, including all the ones in the middle that haven't been drawn. The left edge is right there at 24.5, while the right edge will be over here at 33.5. And so that's why we will have the edges here to be at 24.5 and at 33.5. Okay, so that is the normal approximation that we're going to use. The next thing we do is we have to convert to standard units in order to be able to use the normal curve. So the next thing that we do is figure out the values of mu and pi. Mu, the expected value, is equal to n times mu, or n times pi, pardon me, which is equal to 50 times 0.6, which is 30. The standard deviation is equal to the square root of n times pi times 1 minus pi. Which equals the square root of 50 times 0.6 times 0.4. And then I'll use Excel down here at the bottom to do that quick calculation. So that's equal to the square root of 50 times 0.6 times 0.4, which is about 3.464. So 3.464. Okay, so now that I have the mean and the standard deviation, I will now use that information to convert the x here into standard units. So with that information in hand, let me get rid of that now. Using the 30 and the standard deviation that we see on the screen here, this probability involving the bell curve can be converted to something involving a standard normal distribution with a z in the middle. Z will be greater than or equal to 24.5 minus the mean of 30 divided by 3.464, and z will be less than or equal to 33.5 minus 30 divided by 3.464. Taking both of those endpoints, 24.5 and 33.5, and converting to standard units. So equals the probability that z is between, okay, and I'll do this calculation in Excel at the bottom. So right here we have 24.5 minus 30 divided by 3.464, that's a 1. And at the other side we have 33.5 minus 30 divided by the standard deviation. So those are my cutoffs there. So let me write those down on the calculation here. Negative 1.588, and that's greater than or equal to that. And z is going to be less than or equal to 1.010. Okay, then we use either Excel or a graphing calculator to compute this probability. So that'll be equal to norm s dist of the larger number, A1, minus norm s dist of the smaller number, C1. The area to the left of 1.01 minus the area to the left of negative 1.588. So let me draw the picture here just to see how that works. There's your bell curve. I want the area to the left of 1.01, so that's going to be all of this. But I will subtract off, in red, the area to the left of negative 1.588. So it's going to be all the black stuff minus the red stuff will leave me the area in the middle between negative 1.588 and 1.01. So hitting enter, I get the answer, which is 0.7877. So to 4 decimal places, the answer is 0.7877. So that's the answer using the normal approximation. I want to point out that it is perfectly possible to do this problem. If the question does not say that you have to use the normal approximation, then it is perfectly acceptable to use the binomial distribution to do this problem. So in red over here on the side, let me do an alternate way of doing the problem. This is equal to the probability of 33 successes or less minus the chance of 24 successes or less. So the first probability says I need to have 33 successes or less, but I don't want to have 24 successes or less. And so both of those probabilities can be computed using the binomial distribution. So let me type that over here. So this is the approximate. Let me put it like this. That's the approximate answer using the bell curve. The exact answer can be obtained by doing binom dist 33 50.6 true minus binom dot dist 24 50.6 true. The chance of, right here, 33 successes or less if you do something 50 times with probability 0.6, minus the chance of 24 successes or less with the same numbers, 50 and 0.6. And so this would be the exact answer using the binomial distribution, which is 0.865. So basically the two answers agree to 3 decimal places, which is a very good accurate approximation using the bell curve.